a tracking system, but anyhow, just go on. Okay, so you should see my screen in a second. The recording has started. Second window. Are you able to see my screen?
Yes, ma'am.
Okay, great. So the topic of today's class is to tell you something about canonical transformations. Now, before I tell you what I mean by that, perhaps it's familiar to some, I would like to do a very simple problem, okay? So let's take a 2D plane. I'm going to pick some point, which is my origin, that's my reference point. And from this origin, I have a bob of mass m, which is tethered to this origin by a spring, okay? And this is just 2D plane, so I don't have to worry about gravity and so on. And let's say the spring constant is k, the unstretched length is 0, okay? So any positive x or y is it constitutes actually stretching the spring, okay? Now I want to write out the Lagrangian. How many degrees of freedom does the system have?
Just one, right?
How? I said this is a 2D plane.
2.
Yes, it's 2 degrees of freedom. Why? Because this is not a rigid rod. You see, if it was a rigid rod, it would be 1 degree of freedom only, right? It can only rotate. However, this can move and it can rotate. Absolutely. So it has 2 degrees of freedom. Is that clear to all?
Yes,
Now, I can choose this 2 degrees of freedom to be, I can use any coordinates to write this system. So what I'm going to do is to first try the Cartesian coordinates, okay? That is x comma y. So if I do that, the Lagrangian is 1/2 m x dot square plus 1/2 m y dot square. This is a system where the Lagrangian can be written as a t minus b. Then you have 1/2 kx square minus 1/2 ky square. Agreed? Yeah. Now, I could have equivalently chosen plane polar coordinates, r and theta, right? Do you use r and theta or do you use rho in class?
Sir used to use
R and phi.
R and phi, is it? Okay, I just want to stick to the same notation. Thank you. So let's call it r and phi. Okay, r is the radial distance and phi is the azimuth. Okay. Now the angle that it makes with respect to the x-axis, this is your x-axis and this is your y-axis. Okay. So now and this is phi. So therefore I can write the same Lagrangian as 1/2 m r dot square plus 1/2 m r square phi dot square minus 1/2 kr square. Agreed? Yeah?
Yes, ma'am.
Yes.
Okay. But there is a big difference. So and the problem as is in any of these coordinates is absolutely the same. You get the same equations of motion. You will get the same answer. But choosing the right set of coordinates which exploits the symmetry. What is the symmetry here? The potential is a kr. It depends only on r. It's a central potential. So if I use plane polar coordinates, this symmetry becomes apparent. When this symmetry becomes apparent, it is very easy for me to tell something very powerful about constants of motion. Correct? What is it? Because it's a central potential, I immediately know that phi is a cyclic coordinate. isn't it? Which implies P phi, which is the partial derivative of the Lagrangian with respect to phi dot, equals constant. Why? Because the Euler-Lagrange equation for the phi variable is d by dt partial L partial phi equals partial L partial phi dot, right? And since the Lagrangian does not depend on phi, which is the
Man,
meaning of cyclic, this term
is
vanishes.
it
Absolutely. Tell
the
me.
Man,
Oh, I made a mistake. I'm sorry. I made a mistake in writing. Yes, yes, yes. Sorry. Yes. Sorry. This is what I wanted to write. Absolutely. Yeah, correct. Good. Yeah. So immediately this term vanishes. Okay. So this implies that P phi dot is 0 or P phi is a constant. Okay. That is not apparent if I use Cartesian coordinates, and there is nothing wrong with it. I could have used Cartesian coordinates and I would have eventually stumbled upon this fact. I would have got the z component of the angular momentum, the same p phi written out in Cartesian coordinates. I would have got it to be a constant. Okay, and there is no doubt about that. Okay, but you see, there is a power in choosing your coordinates right. So therefore, this is rather elementary that given a problem, you always want to use symmetry to figure out the right set of coordinates to use. Okay, so here, and if you are given a set of coordinates, let's say qi, pi, so I'm just going to call it, this denotes what? Q1, Q2, and so on, up to Qn for a system with n degrees of freedom, P1, P2, and so on up to Pn. Okay? So if I'm given a system, so this shorthand denotes this. If I'm given this, I can always switch to another set of coordinates. And I'm going to switch to another set of coordinates, A, because it's going to make it much easier for me to solve the problem. It's going to, and therefore it's guaranteed that such a switch is going to give me some insight, pretty much like this example, where instead of working with a Cartesian coordinate, switching to plane polar immediately gave me this insight that phi was cyclic, and hence I see, well, this is a central potential. Of course, P phi has to be a constant of motion. So it told me that instantly, right? So therefore, there is a reason for you to want to go from one system of coordinates to another. And whenever we make a change in the coordinates in phase space, there is also a corresponding momenta you have to reckon with, because finally the dynamics takes place in phase space. Okay. Now the question that we will address in this class, hopefully by the end of this class, is to understand what sort of conditions do I need to impose in order to go from a set of coordinates little qi, comma little pi, to capital Qi, capital Pi, where when I put the suffix I usually mean that I have more than 1 degree of freedom. Otherwise, I will just drop the suffix, then it is a system with 1 degree of freedom. Is my notation clear to all?
yes, Miss. Miss, I
Okay,
had a question. I had a
absolutely.
question.
Please tell me. Please tell me.
Yeah, so in this particular system that we just solved, it was easy and simple. We could understand that if we convert it to polar coordinates, then it would be
Mm-hmm.
easier to look at what is the cyclic coordinate.
Correct, correct.
So, in for any general system, how do we figure out
That's a
that?
that's a that's a question which is very, very hard to actually tell you. I will talk about one way of setting up this transformation, but usually you will use something called generating functions for these transformations. So we'll come to that, okay? But in the end, it's very, very the one thing that I can guarantee is that there is no unique way for guessing this. This is some inspired guess which allows you to exploit the freedom. In other words, I mean, for a canonical transformation, it will become clear towards as we go on with the lecture. But in general, choosing a set of coordinates is pretty much dictated by symmetry. Okay, so when you ask a question as general as that, I would say, well, you have to look at the symmetry of the problem. Now, if you ask, and the symmetry pretty much dictates what you need, what sort of coordinates you need to choose. If I have cylindrical symmetry, I choose cylindrical coordinates. If I have spherical symmetry, I choose spherical coordinates, and so on. Okay,
So what
so
you mean
that's
is that for a particular system, I can make an educated guess about the
you
type of
can
symmetry
make.
that can be there, and then
Yes,
we can.
yes. But by the end of the class, you will also be stumped by some of the quote unquote educated guesses for some things I'm going to tell you. Okay, but hang on. All right.
Okay, thank you.
Okay. So now, um, yeah. So what that's the kind of question that I want to ask. So the first thing that I need to know is that now all of you are familiar with Hamilton's equation. I was told, right? So the first thing I know is that whatever change of coordinates I make, it should not affect the equations of motion. Here, that's what I said. That's what I started out as a guarantee that, oh, it doesn't matter which set of coordinates I use. I'll define the corresponding momenta. Instead of the Lagrangian, I could have worked with a Hamiltonian, and I would still get the same conclusion about the motion, equations of motion, which I hope in this case I can actually solve given a set of initial conditions, which is not something you're always guaranteed. Okay. So therefore, um, um, uh, you know a priori that given a set of QIs and PIs, I know that QI dot is what? Partial derivative of the Hamiltonian with respect to PI, and PI dot is minus partial derivative of the Hamiltonian with respect to QI. Agreed? This form cannot change. What does this mean? So form of the Hamilton's equation cannot change. This implies whatever I call my new coordinates, capital QI dots, better be partial derivative of some other Hamiltonian. The Hamiltonian can change, but what I'm interested in is the equations of motion with respect to the new momenta. Capital PI should be exactly the same, has to have the same form. So PI dot is minus DH prime DQI. Is my motivation clear? Now transformations and such transformations where the form of the Hamilton's equations don't change guarantee that my equations of motion are going to be the same, and that's absolutely necessary. And such transformation have a special name. They are called canonical transformations. Okay? Now it turns out that a transformation from a set of coordinates qi, pi to a new set of coordinates capital QI, capital PI, where capital QI is going to be what? A function of the little QIs and little PIs, correct? And capital PI is also a function of little QI and little PI, and therefore a transformation is canonical if I can show that the Poisson bracket calculated with respect to QI, PI, the little QI, little PI is the same, equals 1. Okay, so if I have a system with 1 degree of freedom, I would have gone from a QP to a capital Q, capital P. Capital Q, capital P are functions of phase space variables, little q, little p, of course. So therefore, I am guaranteed if the transformation is canonical, and so when the transformation is canonical, I am guaranteed that the partial derivative of capital Q with respect to little q into partial derivative of capital P with respect to little p minus the partial derivative of little q with capital Q with respect to little p, and this is 1. Okay, this is in fact a definition of canonical transformation, and it is related to the fact that the Jacobian of the transformation going from little q, little p to capital Q, capital P is unchanged. It's 1. Okay, so that's what it translates to. So now, if I have more than 1 degree of freedom, what happens? If I have a Qi, Pi, this is going to be a summation, right? This will be capital, I should just use N. Capital P, notation, capital Qn, into capital Pi, capital Pn minus capital Qi, capital little pn. I'm saying capital, I'm sorry, I meant to say partial derivative with respect to little pn, then partial derivative of capital Pi with respect to little qn should be 1. Now, as an exercise, you all would have done this. I mean, you all would have changed from, let's say, when you go from Cartesian. So let's look at the same transformation that we did. From Cartesian, there in that example, I went to plane polar, correct? But I can always write R as a function of X and Y. And that's what I mean by saying this capital Q is a function of little q, little p. Capital P is a function of little q, little p. And that's the same. That's all the statement I'm trying to make. So you have this, then you have phi to be tan inverse of y over x. Then similarly, I will have PR. I'll also have p phi. Okay. Now, what you can show is that R, PR with respect to x, y, and so on should be 1. I leave it as an exercise. It's rather straightforward algebra, so please try to show this. Okay, so therefore, when you go from plane polar to Cartesian or spherical polar to from Cartesian to spherical polar or whatever, these are all canonical transformations. Okay, they leave the equations of motion unchanged. You'll have the same form for the Hamilton's equation, because rightly, as we saw in the first example with the Lagrangian, you went from a Lagrangian defined in Cartesian to a Lagrangian written out with plane polar coordinates. The same thing. The Lagrangians would be different. The Hamiltonians will look different, but the equations of motion, the form of the equations have to be the same. Okay, the content has to be the same. Okay, so that is absolutely crucial. Now let us see some. So why would we do this? Okay, the answer goes back to exactly the example that you saw. You want to find out if I can somehow find a transformation that is going to give me cyclic variables. When I have cyclic variables, what happens? The corresponding momenta becomes a constant of motion. So therefore, in phase space, the dimensionality where you actually have, motion, it starts decreasing. Okay, so therefore, you don't have to, you don't have a large dimension in which your dynamics takes place. That dimension starts to go down. So therefore, getting these constants of motion is very, very crucial. It's one of the most important things that you would do in any problem in classical mechanics. Well, it in fact holds for other areas as well, because when you have symmetries, you have constants of motion in classical physics, and whereas in quantum mechanics, it becomes good quantum numbers, okay, which will label your states. So now, one obvious advantage, of course, is that I want to get cyclic coordinates. So what happens if I can somehow go from all Qi's, Pi's set to another set, capital Qi, capital Pi, okay, and this has a Hamiltonian H, this has a Hamiltonian H prime, and let's say H prime is such that all Qi's, the entire set Qi's, are cyclic. What does it mean? Partial derivative of H prime with respect to Qi is 0. Okay, which means Pi dot is 0 for each and every I. So therefore, I have n constants of motion. This is not something that comes by very easily, but if such a thing comes, such systems are supposed to be integrable. Okay, I'm just mentioning this in passing, but you'll get back to that later with Suresh. So that is so then that makes my problem easy, right? Because then what are the PIs? PIs are going to just depend on some initial condition at some let's not say I can put some time t0 and perhaps at the time t equal to 0, t0 equals 0. So then all it depends on are just constants. They just determined by initial conditions. Now what happens to the QIs? The QI dot, of course, will be partial derivative of the new Hamiltonian H prime with respect to Pi, and let us say it is some omega I. Okay, and therefore Qi at a later time is omega it plus some alpha i's, which I can again determine using initial conditions for the Qi. So you see, it's so easy to solve such a system. Okay, and that's why such systems are hard to come by. But if you can come up with a canonical transformation which does this, then you're really set. And you will see that such transformations will impose very severe constraints on the form of the Hamiltonian. Okay, but moving on. So in general, the take home lesson is that if I go from a set of coordinates Qi, Pi, which I call old coordinates. Oh, too many O's in my coordinates. Old coordinates and old momenta to a new set. Then this transformation is canonical if and only if I can show that the Poisson bracket structure with respect to the QIs and PIs remains the same. Okay. Okay. So now let's see some example. Okay, I'm going to work with systems with 1 degree of freedom. It's very nice and easy, which means I have a generalized coordinate Q. The dimension of the phase space is 2. I have a generalized momenta P. Okay, now I want to go from this set to a new set, capital Q, capital P. I'm going to give you one transformation. Little q goes to capital Q. Now, little p goes to capital P. Is this a canonical transformation? Can you compute the Poisson bracket and tell me? How would you do that? What would you have to do? Anybody?
Ma'am, we would take the Poisson bracket with respect to the old coordinates and then
Okay.
substitute
Oh,
the new coordinates in place of the.
yes. So you have to do this, correct? I'm not going to
Yeah.
speak it because if I speak it, I speak wrong things. So you know what I am saying, correct? This is absolutely what you're saying, correct? So then what is partial derivative of the new q with respect to the little q? 1. Partial derivative of new p with respect to old p? 1. And this term is 0. So therefore it is a canonical transformation. Okay. Now let's try one more. Let's try little q going to capital P.
Yes, in that equation it will be del P del Q in the last one.
Yeah. Thank you. Thank you. Yes. So little q going to capital P, then little p going to, okay, little p going to capital Q. Will this be canonical?
No,
Compute. No. What do you need to do? How will you fix it?
minus q. P going to minus q.
Little p going to minus q, or the other way around, right? Little q can also go to minus p. There's nothing unique about this. You see, it's just a transformation. So the first transformation that we saw is an identity transformation where the Q's remain Q's, the P's remain P. This is one where the role of P and Q is exchanged, but it will be exchanged with a relative minus sign. Okay, so that the canonical structure is preserved, which means the Poisson bracket structure is preserved. Is that okay, everyone? Now, there is another way to look at, now what we want to do is, of course, here, I have sort of given you the transformations, right? So the one question, which was perhaps stated right in the beginning, was how do we even come up with these transformations? And as I said very loosely, well, the symmetry dictates and so on and so forth. But now it turns out there is a way in which you can figure out what your new variables and how your new variables and your old variables are related, and how the new Hamiltonian and the old Hamiltonian are related. It all begins with with action. Okay, which is what you started even in the first place to set up the Lagrangian and later the Hamiltonian. All right. So therefore, let's start with the action. So the action is an integral going from T1 to T2 LDT. Okay. Now, if I set the variation of action to go to 0, that's going to pick out the classical trajectory. Okay, and I vary the action such that the end points are fixed. Endpoints are fixed, I should be more precise, variations of Q at the endpoints. I'm only taking a system with 1 degree of freedom. Okay. So now, of course, you know that if I do this variation with the Lagrangian will be a function of Q dot and time. I get the Euler-Lagrange equation, and I can also do the same thing with a Hamiltonian, because how are the Lagrangian and the Hamiltonian related? They are related by a Legendre transformation, right? It's PQ dot minus H, correct? The Hamiltonian is always a function of P and Q. So the Q dot, P, Q, and let me write it properly. Q, P, and T. Correct? This is what the Hamiltonian is. So now, so given this, I'm going to plug this in. So I have the action S, which goes from T1 to T2, PQ dot minus H, dt. So therefore, if I vary the action, then I'll vary this integral. Correct? And then you have PQ dot minus H dt. So then that's a variation in these guys. So T1 to T2, delta of PQ dot minus delta of H dt, which is T1 to T2 dt, delta P into Q dot plus P delta Q dot minus partial derivative of H with respect to Q, delta Q, minus partial derivative of H with respect to P, delta P. Correct? This is what you would do. Then what would you do? You would integrate this part, this term, this integral by parts, and that's what gives you the Hamilton's equation, right? So this should in fact give you T1 to T2 dt delta P into Q dot minus partial derivative of H with respect to P plus delta Q into P dot plus partial derivative of H with respect to Q. Okay, and that gives you the Hamilton's equation, because these variations are considered to be independent in phase space. Because when you go from the Lagrangian to the Hamiltonian, the variations are no longer done in a configuration space, but it is done in phase space. And that leads to your Hamilton's equation, which is by now very familiar to you. Okay? Now, of course, the same has to hold if I go from the old set QP to the new set capital Q, capital P. Therefore, what I would expect is that integral T1 to T2 PQ dot minus H dt has to be related to has to be related to integral T1 to T2 capital PQ dot minus H prime dt. But you know that this need not be just equal. I can always add to it a total derivative, right? Because this is equivalent to saying that L equals some new L prime, but it need not be L equal L prime. You can always add to it a total derivative of a function f. Okay. Now, what can this function depend on? I claim that the function depends on the old coordinates, new coordinates, and perhaps time. Okay. Now, this function, yes.
What happened to the time dependence of the Hamiltonian in that delta when you took the delta of h in the second line?
Where have I?
The previous page, yeah, this one.
But no, because your variations are only with respect to the endpoints. Time is left as is, right?
Okay, yeah, get it.
Yeah, okay. All right. All right. So now, so then you see, you have this, so this is precisely the condition you have. Therefore, you have PQ dot minus H equals capital P, capital Q dot minus H prime plus df dt, where f is a function of little q, capital Q, and t. And I claim that this function f generates, is called the generator, is called a not generator, it's called a generating function. Okay. In fact, it's called F1. I'll tell you why it's F1. I mean, that's just a name. Okay. It's a generating function. I'm just going to use the symbol. Go ahead and use the symbol F1 there. And this generating function relates the old coordinates and the new coordinates. Therefore, from this generating function, you should be able to get some relationship between the old, which will, you'll have some relationship which gives you the old momenta and the new momenta, and you hope that all these relationships are such that it can be inverted, so that in the end little q little p can be written in terms of capital Q capital P and vice versa. Why is that important? This invertibility is important so that you only know the form for the old Hamiltonian. You have to know the form for the new Hamiltonian. When in doubt, think of what you do with when you go from Cartesian to plane polar. Okay, for the first problem, the sample problem that I said, you only knew the, let's say you just knew the Hamiltonian for the system in Cartesian coordinates. If I want to change coordinates to plane polar, what do? I use the relationship that the Cartesian coordinates bear with the plane polar coordinates, and then rewrite my Hamiltonian to get the new Hamiltonian or the Lagrangian, as the case may be. Okay, so that's exactly what I need to be able to do. All right. So now let's go on and use the chain rule and calculate this guy here. So this is PQ dot minus H prime plus partial derivative of F1 with respect to Q dot plus partial derivative of F1 with respect to capital Q dot plus partial derivative of F1 with respect to T. Just give me 1 second, okay? Just give me a second. Yeah, can you still see my screen?
Yes, ma'am.
Okay, good. So this is what we have here. All right. Now, such an equation can hold only if I can equate the coefficients of q dots, little q dots and little capital Q dots. Okay, so therefore from this I get the condition that little p equals partial derivative of f1 with respect to q, capital P equals minus partial derivative of f1 with respect to capital Q, and minus h equals minus h prime plus df1 over dt, or h prime equals h plus df1 over dt. What good does it do? What it does is that if I give you a form for this generating function, f1, then you get little p, capital P. Little p will be a function of little q, capital Q. Capital P will be a function of little q, capital Q. But you can invert them. Okay? You can invert them and then get little p, little q in terms of capital P, capital Q. Therefore, you plug it into your original Hamiltonian H, you will get the new Hamiltonian H prime. So just to, sort of, when you see abstract things like this, it's important to immediately see an example. Okay, so I'm going to give you well, let's take, actually it's good to do an example at this point. So let's take the Hamiltonian to be p square plus q square by 2. So this is your oscillator, harmonic oscillator, where I've set the mass and the omega to be 1. All right. Now I'm going to give you this f1, which is a function of little q, capital Q, which is 1/2 q square cotangent 2 pi q. Of course, you see, this is a problem that you already know the solution to, and I will tell you how you'll get the solution with this as well. But let's go on. Okay, so this is my this is the generating function. Now, can you use your relation and get for me little p and capital P? Please go ahead, do it, and tell me what your little p and capital P are. Do it right now. What is little p? You have to take a derivative with respect to little q. Little q comes only here, so it can only be q cotangent 2 pi capital Q. Okay? And what is capital P? Capital P is minus partial derivative of f1 with respect to capital Q, which appears in the argument of cotangent. Right? So what would that be?
Q square by 2 cosec square 2 pi q into 2 pi.
Into, there's going to be, is it a cosecant? Oh, cosec. That's what you meant by cosec. Okay, I thought you meant cosine. So sorry. So you will have a pi for sure, q square, because that remains as is. Then the factor of 2 will cancel. Then the derivative of cotangent is going to give me a cosecant square 2 pi q. Correct? Because of course with a minus sign, and I have my minus sign there. So this is what it is. All right. Now, will these relationships allow you to define little p and little q in terms of capital P, capital Q? You can invert them, correct? What is little q from here? From this, I can say little q is capital P over pi under square root sine 2 pi q. Correct? So then I go plug it into little p. What is little p? Little p is q into cotangent. Cotangent is cosine by sine. So the sine will cancel. So therefore, this will be capital P by root pi into cosine of 2 pi q. So you see, it was important that the function is invertible. So when is a function invertible? As long as, so if I have a function and I want to invert it, I cannot have the slope to be 0. Correct? So if I have a function, some function f of x and x, if I have a function like this, given an x, I can tell you what the f of x is, but I can't invert it. So I need a function where f prime of x is not equal to 0. And that's precisely the condition that these partial derivatives of f1 with respect to little q and capital Q has to satisfy. Okay, so now therefore you see the function that I have here is nice and invertible. I am able to get little p and little q as functions of capital P and capital Q. Agreed? Now let's plug it back in. If you plug it back in into the Hamiltonian, what do you get? The Hamiltonian first was just a p square plus q square by 2. Now I need my h prime, which means take h in the place of q. Please use the function that you have figured out in terms of capital P, capital Q. This is what you have to do. So can you tell me what the h prime is? What is h prime?
2p by pi.
Sorry?
P by pi.
It is p by pi. Very good. Is it cyclic with respect to q?
Yes.
Yes, it is, right? So therefore, just give me a second. Hello? Yeah. So, so what happens to Q? So let's do the P dot, right? Because I first want to, I know that it is cyclic. Therefore, I take dH prime dq is 0, which means P dot is 0, correct? Or P is a constant. So let's call this constant some C, which is determined by initial condition, okay? Where this is a constant determined by initial conditions. Now what happens to Q dot? Q dot is partial H over partial P. So if it is partial H over partial P, then this is going to be 1 over pi. But then that makes it very easy to solve Q, correct? So what is Q of at a later time t? It is going to be some t over pi plus some initial condition, let's call it some alpha at some time t0. This is also some c at some time t0. Oh no, maybe I should not call it t. I'm just going to call it p0. Okay, that's nice. Let us say that this is such that it is 0. It's just a choice. Okay, it doesn't do anything to me. Now, if I go back to my relationship that I have for little p, little q, what is little q? Little q is capital P over pi into, it was the sine guy, right? To sine of 2 pi sine 2 pi q. So therefore, if I put this, what is this? It is some p0 over pi sine of 2t. Have I got my signs right? Perhaps I have. It should be a 2 pi. P over 2 pi. I missed the 2. So there is a 2 there. There is a 2 there. So this 2 goes away. Sine t. Similarly, what is p? Capital P over pi cosine of 2 pi q, which implies that capital P is P0 over pi cos t. Omega is 1. Okay, so therefore you see I have got exactly the solutions I know, and what I have done is to illustrate the whole idea of one motivation for doing canonical transformation, which is it allows me, if I have a generating function, I just used the definitions that I just set up and to figure out the relationship between little p capital P to little q capital Q. I inverted the relationship to obtain little q in terms of capital P capital Q, in terms of the new variables. Then It was rather straightforward. This generating function does not depend on time. So therefore, the new Hamiltonian will just be the old Hamiltonian written in terms of the new variables. And if I have this relationship between q, little p, and capital Q, capital P, then I will get the new Hamiltonian H prime. Is that all right? Yeah?
Yes, miss. Miss, we are not bothering about the dimensions, right? Okay.
Which one? I said omega is 1. Otherwise, you'll have
Yeah.
omega because time, right? You think of time as some scaled time, okay? Dimensionless
Yeah.
thing which already has an omega there. That's why I said omega. Omega is 1. I kept telling you. Otherwise, I would have had to put an omega there. Then my generating function should also carry this omega correctly. Okay?
Yes, miss.
All right. So, and that's not all you can do. Okay. So, what else can you do? So now you see, I have very suggestively, I used this function f1, correct? So what I'm going to do is go back to my definition. I have pq dot minus h equal capital P capital 2 q dot minus h prime plus df1 dt, which is a function of little q, capital Q, and perhaps time. This is what I started with, right? Now what I'm going to do, I'm going to do the following. If I consider d by dt of pq, what is that? P dot q plus p q dot. Therefore, I can write pq dot as d by dt of pq minus p dot q. Agreed? Substitute it here. If I substitute it, it is d by dt of pq minus p dot q minus h equals capital P q capital Q dot minus h prime plus df1 dt. Okay. Now this is p dot q minus h equals capital P q dot minus h prime plus d by dt of f1 minus pq. Agreed? Yeah? Now, let's look at this guy. I'm going to call f1 minus pq as some new variable. I'm going to call it f3. Okay, for reasons that is not at all obvious. It's just a name. I like the letter 3, the number 3. I'm just putting 3 there, which is f1 minus little p, little q. All right? Now, this is not any ordinary functional relationship. How is little p related to capital F1?
It's Legendre transform.
Absolutely correct. This is a Legendre transformation, right? Therefore, what have I eliminated? By doing this, having this defining relationship, trades the little q that is there in F1 for little p. So, I want to write it in full glory as little q, capital Q t minus pq gives me f3, which is a function of little p, capital Q, and t. Okay? Now, of course, I can get relationship between different variables. So now what I'm going to do is to start with this guy. All right? So what is this now? Minus p dot q minus h, correct? Equals capital PQ dot minus H prime plus d by dt. I just called it F3. It's a convention. Little p, capital Q, and t. Is this correct? Okay. Now, let's try to find out what should we do next. This will be PQ dot minus H prime plus this will be df3 dp into p dot plus df3 dq into q dot plus df3 dt, correct? Because at the end of the day, I have to tell you how to get the little q and capital P in terms of derivatives of F3. That's what we did with F1. So I'm going to repeat the same exercise here. All right. So then what happens? The only way such an equation would hold is immediately you know that Q is going to be minus dF3 over d little p, and capital P is going to be dF3 over dQ. Have I made a sign error or something? No. Okay. Yeah, I'm all right. I don't see any sign error. Yeah, I'm okay. All right. There has to be a minus sign, I guess. Because there is a Q dot, there has to be a minus sign. And then that immediately tells me the new and the old Hamiltonian, H prime equals H plus dF3 over dt. Now I can play this game further. Correct? What I can do next is take d by dt of PQ. That will be P dot Q plus QP dot. Okay. Now, what do? I go back to my defining equation, which was PQ dot minus H equals capital PQ dot minus H prime plus d by dt of F1, which is a function of little q, capital Q, and T. Now I insert in the place of, I have made a mistake. I've written the same term two times. P dot Q plus PQ dot. So I just have to trade in for PQ dot. If I trade in for PQ dot, I'll have d by dt of PQ plus P dot Q minus H prime plus d by dt of F1 Q, Q, and T. Okay, which I will now combine, which I will write this as, what should it be? P dot Q. So P dot Q minus H prime plus d by dt of F1, a function of little q, capital Q, and T plus PQ. Okay. What is capital P now? Capital P is minus dF1 over d capital Q. That is the relationship. So hence, this is once more a Legendre transformation. And I get a new generating function, which I call F2 of little q, capital P, and T. So I've traded the capital Q for capital P. So then I have PQ dot minus H is capital PQ minus H prime plus dF2 dt. What do you have? Okay, so it is dF2 over dQ Q dot plus dF2 over d capital P P dot plus dF2 dt. This implies that little p is dF2 dQ. Then capital P is what? Capital P is, no, capital Q. I somehow feel I have made an error with my sign, so please verify. I have capital Q to be dF2 dP with a minus sign. I have a feeling this has to be plus sign. Maybe I've made a sign error. You could check. So then this immediately, and of course I will have H prime to be H plus dF2 over dt. That gives me one more generating function. Okay. Now I can play the same game where I use both PQ, d by dt of PQ and d by dt of PQ dot to get one more generating function, which would be a double Legendre transform, where I trade both little q, little capital Q for little p and capital P. That is the fourth generating function. So therefore, you see, I have now got for you four generating function, capital Q and time, then F2, which is a function of little q, capital P, and time. F3, that's why I chose these numbers, because that's the convention. Otherwise, what it is a function of is more important. That is a function of little p, capital Q, and time. Then F4, which is a function of capital P, capital Q, and time. No, sorry. F4, which is a function of little p, always old and new, capital P, and time. Okay, these are my 4 generating functions. Now, I want to just go back and do something. You had F1. Suppose I write this as little q, capital Q. Can you get for me the P and the capital P? Little p was partial F1 partial Q. Capital P was minus partial F1 over partial Q, capital Q. Then what is little p now? Little p is capital Q. But what is capital P? This is the transformation that we started with, right? One of the examples we started with where I said, well, if little q, I think I just said little q goes to P, but I said you could do it the other way around. Here you say little p goes to Q. Then you ask, how does little q transform? Little q goes to minus P, so that the transformation is canonical. So here's a generating function that generates exactly that transformation, where the q and p's are interchanged but with a relative negative sign in order to preserve the Poisson bracket. Okay? So while this seems at the moment motivated more towards solving a problem, and in fact, I showed you an example where I solved the oscillator, which you can anyway solve by this canonical transformation, got you a Hamiltonian where the coordinates were cyclic, and that allowed you a very simple solution, but that's really, I'm not achieving much because it's already a problem that's easily solvable. However, that illustrates the technique that I want to establish. However, there is something very interesting and deep about canonical transformations, which is time evolution. Time evolution is by itself a canonical transformation. Why? Because let's assume that the system goes from some time t to a later time t plus delta t. I'm going to think of it as an infinitesimal transformation. Okay. So now what happens? The Hamilton's equations are preserved from the new set, from this at the time t as well as at the time t plus delta t. That's by construction. And therefore, since the trajectories change, you go from a set little q, little p, to a new set capital Q, capital P, which is actually t plus delta t and little p of t plus delta t. So therefore, you can actually view time translations as canonical transformation. Okay, so with that, I'm going to stop because it's also time. And so just to recap, what you have seen, or rather what I want you to take home, is that just as you, given a problem, you always want to choose the best set of coordinates to work with. Okay, and the set of coordinates you want to work with should be such that the problem can be easily solved, and therefore you want to work with the coordinates where you can get many of the generalized coordinates to be cyclic, and this is one such example. Okay, and when you do a transformation in coordinates, there is also a transformation in momentum. And as I told you, this change from so therefore you can ask if I when I do this, when I view this transformation as a transformation from an old set to a transformation to a new set, when is such a transformation even viable? And viable just implies that I should not do anything to the equations of motion. The equations of motion have to be preserved. So a transformation which does this is called a canonical transformation, which preserves the equations of motion, which means Hamilton's equations. They are called canonical transformation because these are transformations in phase space. And this, by construction, if you can show that I'll say by definition, if you can show that the Poisson bracket of the new variables taken with respect to the old variables, if that is exactly the canonical ones, then you have showed that the transformation preserves the structure of the Hamilton's equation. Now, of course, as an example, you see, I gave you as an exercise to go from Cartesian to plane polar and show that such a transformation is indeed canonical by actually calculating the Poisson brackets of R, P, R, theta, P, theta, and so on. And you can show that this transformation is canonical. But more to the point, you want a way which will allow you to get the relationship between old and new sets of coordinates, the old and the new set of Hamiltonian, and all you have to do is to start with a variational principle, okay? And that's what we did for a large part of the class. My slide is not moving forward, which is start with the fact that the two Lagrangians will need not be exactly identical. They can at best vary by a total derivative of a function f, which I claim is a function of the new coordinates and the old coordinates, okay? And that allows me to set up relationships between, with respect to the, relationship that defines for me the old momenta and the new momenta, if it was this generating function, or equivalently, I can go and set up other generating functions, okay? Then, of course, one can view this canonical transformation, time translations itself is a canonical transformation, and that will be something that will be touched upon later. With this, I stop. Are there any questions? If not, I can switch off the recording. Okay. So since there are no questions, I'm going to I'll stop presenting and I'll turn off the recording.